Video, we present shortly a more general formulation of the linear mixed effect model. So in the previous video, we considered the simple linear regression model where we had only one fixed predictor x, and the same predictor was also included as the random predictor. But in general, we can specify a multiple regression model that looks like the model presented here. So the fixed part includes a total of p predictors, and we have a separate regression coefficient beta for each of them. In addition, the random part can include a total of s predictors, and we have a separate group level coefficient beta 1 to beta s for each of them, and then otherwise we have the residual error in the same way as before. And then we specify the vector of random effects as bi, and that vector includes the random effect from bi1 to bis. So all random effects for this particular group I. And by using similar notations as we have defined before in the linear model, we can specify that the fixed part is a linear combination of vector xij and beta, and in the same way the random random part is a combination of vectors zij and beta bi, and here bi is as we specified here, and zi is specified as the vector that includes the predictors zij1, which is the number 1, and then we have zij2 until zijs. And as I said, this number 1 here, in the same way as we defined the model matrix for the linear regression before the first predictor is commonly intercept. First predictor is the constant 1, so that the first coefficient is interpreted as the intercept. So now when we specify this 1 here, then it means that this predictor here is a random intercept. But we could specify also models where we don't have random intercept, but they are seldom useful. And it's important to define, now that the bi's are the random effects, we need to specify the variance covariance matrix of the random effects. And in the previous model where we had random intercept and slope, the matrix included this part from this matrix. Now we have a total of s columns and rows in the matrix, and it includes all the variances of the random effects on the diagonal, and all of diagonal elements are then the covariances between each pair of the random effects. So this means that this variance of bi, which we can denote by matrix di, includes a total of s variances on the diagonal and a total of s multiplied by s minus 1 per 2 covariances on the off diagonal. So these are, and all these variances and covariances, we don't have any restrictions for them by default, so they all are separate parameters in the model. So if we have, for example, 3 random effects, if we have, for example, 3 random parameters, then the random part is parameterized using a total of 3 variances and 3 covariances. And then we assume that the groups are independent and identically distributed. So it means that the covariance between the groups is 0, and the distribution of them is always the same. So therefore the di matrix is the same for all groups. And therefore we don't use the notation di I, but we denote it by the star, where the star means somehow means that it can be used for any group. So all groups have the same variance covariance matrix for the random effects. And then usually the element of Zij vector, so the predictors of the random part, are a subset of the elements of Xij, that is subset of the predictors of the fixed part. And especially predictor that is included in the random part should be included in the fixed part also, unless there is a specific theoretical reason to drop that predictor from the fixed part. But that is very seldom the case. And if we assume that Xij and Zij are the same, then we can write the model in such a way that we assume that there is the first random effect is associated with the intercept, and then the second random effect is associated with the second predictor of the fixed part, and so on. And the pth random effect is associated by the pth element of the beta vector. So that way we can assume that we have a random slope for corresponding to all of the predictors. So we could also specify the model in this form here. So we have Xij prime multiplied by vector Ci, and here the Ci is a vector with expected value of beta and variance d star. And the Ci is just the sum of vector beta and bi. But this formulation here illustrates that, okay, actually we can think that the fixed part just gives the expected values of the parameters, and then the random part specifies how much those parameters vary around their expected values when we think about or how much the group-specific parameters vary around their expected values. And the expected value is given by this beta vector. And the variance covariance matrix of those differences is then given by the matrix D star. And an interesting application of the model with more than two random effects is the model that includes random effects for category predictors. This is something that we are not going to cover on this course, but those of you who are interested in, especially if you are modeling some datasets where you have categorical predictors, and it seems that the variance of the group effects in different levels of the categorical predictors is different, then you could read the subsection 2.1.4 from the lecture notes package. But this is something that is not like the basic knowledge for the course, but just for those who are interested in.